Right, so today we're going to go through 4.6, sum and difference identities. This should be on about page 256 of your workbook. We're going to continue on. Last time we did trigonometric proofs. We proved identities, and we proved that the left side is equal to the right side for all values of x. And we did that by using some of the tools that we had developed. One of the notable tools that we had developed was Pythagorean identities. Sine squared of theta plus cos squared of theta is always equal to 1. And so then we could have used that and any manifestations of that to use it as a tool to prove these identities. Today we're going to develop a couple of new identities that will always be true. These are called sum and difference identities. When we want to determine exact values for sine, cos, and tan, where tan is not on the unit circle. So here we're using values like 15 degrees or 75 degrees, or if we're talking about in radians, we're talking about pi 12ths, anything that is using those multiples of pi 12ths. Thinking of it this way, if we take 1/3 and we subtract and we subtract a quarter, what do we get? And so if we do that as a fraction, so if I take 1/3 minus 1/4, well, to do this, we have to convert everything into a common denominator. So we would call this 4/12 minus 3/12, which ends up being 1/12. And so really, if we have pi over 3 minus pi over 4, and this is 4 pi over 12 minus 3 pi over 12, ends up being 1 pi over 12. So we can take that approach, that converting all of our radians into twelfths will help us to see how these amounts are just expressed in the sum or a difference of quarters and thirds and sixths. All right, so let's starting off. These are on your formula sheet for this course. So you don't need to memorize them, you just need to be able to use them. And so we have sine of a plus b. Sine of a plus b is defined to be sine a cos b plus cos a sine b. So it looks like a lot. There's a lot going on in there. It certainly is not a straightforward beast. There's a lot in there. And when we look at all of the different manifestations with cos and with tan, with adding or subtracting, there's a lot here if you had to try to memorize this. Sine of a minus b, if we're talking about the difference of two angles, sine a cos b minus cos a sine b. So it's the same formula as sine, and because it's a difference, this ends up still being subtraction. And so with sine, your pieces are the same, sine a cos b, cos a sine b, but now it's adding, then now it's subtracting. Okay, so moving into cos, cos shifts things around a little bit. The formula for cos a plus b is cos a cos b minus sine a sine b. And then for cosine of a difference, cos a cos b plus sine a. So notice that with the cosine formulas, it was cos a cos b, sine a sine b, but when we had our sum of angles formula, this ends up being subtraction. Where we had our difference of angles formula, this ends up being addition, opposite to what it was for sine. And then for our tangent formula looks different, well, because tangent behaves differently in general, and what we have is tan a tan b over 1 minus tan a. And then maybe like we would surmise, formula for tan of A minus B is tan A minus tan B. We change the sign over 1 plus, we change the sign, tan A. So these are all of our new sum and difference identities. We're going to use these by the time we get deeper into this. We will be using these as a tool to prove other trig ratios, other trig identities, sorry. So to start us off, we are going to start slowly, and we're going to start with something like sine 75. Well, so we have to think of 75 degrees as either a sum or a difference of two angles that we know of on our unit circle. And so the easiest way to look at this is, of course, 75 degrees is equal to sine 30 plus 45. Now there's other ways of doing this. We could take something like 120 minus 45 is also 75 degrees. Right, there's going to be lots of different ways of getting there. So we could use your subtraction, your difference formula for sine. But let's just keep this one straightforward, and we'll do this one with sine 30 plus 45. So by following this formula up here, by following this first one, that sine A plus B is sine A cos B. All right, so if your A is 30 and B is 45, so this ends up being not too bad, sine 30 cos 45 plus cos 30 sine 45. Those are all degrees. And so now we look at what we have. So 30 degrees. At 30 degrees, sine is vertical, sine is 1/2. We also have 45 degrees. So cosine of 45 degrees is how far over 45, 45, 90 triangle, and is 2 over 2. Remember that root 2 over 2 is equal to 1 over root 2, and so you could use either of those. I usually like to work with root 2 halves, so let's do that. All right, so plus cos 30 now, so cosine of 30 is now the long side of that triangle. It's root 3 over 2, and sine 45 is root 2 over 2. We add this all together. We've got a common denominator of 4, and we end up with root 2 plus root 6 over 4. Question number 2. Exact value of cos 15 can be written in the form of a plus root b over c. So here it's giving us the form of what our answer should look like. So this ends up being a little bit of a clue, a little bit of a roadmap of what you should be able to simplify it to. And then once we get it simplified to there, you answer A, B, and C. In this question, make sure that we state what A, what B, and what C are all equal to. This would easily be set up on a diploma exam, like a numerical response question, where it asks you to put A, B, and C in your in the first 3 boxes. So something like that. So to start off this question, we have to think about, so 15 degrees. How could we do 15 degrees? Well, 15 degrees, so certainly we're going to use subtraction, lots of different ways of doing it, but maybe the simplest one ends up being, let's convert 15 degrees. Cos 15 degrees is equal to cosine of, oh, I don't know, something like 60 minus 45. So that difference is 15 degrees. Now we're going to use our cosine difference formula. And our cosine difference formula looked like this. Cos A, cos B. So let's call this cos 60 degrees, cos 5 degrees. And then our next part was plus sine A, sine B. Sine 60 degrees, sine 45. We're wanting to think of what happens with our 60 and what happens with our 45. So at 60 degrees, the cosine is 1/2. At 45 degrees, easy equals both root 2 over 2. Sine of 60, vertical side of that 30, 60, 90 triangle standing up. So root 3 over 2, and then sine 45 is root 2/2. We add all this together, this ends up being root 2, root 6, 4. Again, the same answer as before, but make sure that we answer what the question is asking for. Therefore, A is equal to, make sure that we're in this form, that it looks like that, and it does. A is equal to 2, B is equal to 6, and C is equal to 4. This question, your answer shouldn't differ no matter what we use for our two angles that differ by 15 degrees. So whatever two things that we come up with, it could be 135 minus 120 is 15 degrees. And we could, there's lots of different ways of getting there. Keep in mind also that if you did this a little differently and you end up getting root 6 plus root 2, so if you got these the other way around, then A would be 6 and B would be 2. Because they're just adding, of course, that would be acceptable. That would still be correct. Number 3, the exact value of tan 105 can be expressed in the form of negative A minus B, negative A minus root B, and finding our values of A and B. So 105 degrees tan, 5 degrees. Let's call this 60 plus 45. And we're going to use our tan sum formula. That ends up being 60. It's tan 45 all over 1 minus tan 60. 5. So a little less straightforward because we have to now remember our tangent of 60. Remember, tan 60 is root 3, whereas tan of 30 degrees would have been root 3 over 3. Tan of 45, the one that's right in the middle, nice and easy, is just 1. So that's what we have to keep straight. Tan 60 ends up being root 3 plus 1 over 1 minus 3 times 1. In this course, it's okay if we leave our denominators not rationalized, but in this question, it is asking for us to get it into this form. So we have to get it to look like that form. So how do we do that? That was in 20-1 last year. We multiplied by the conjugate of this denominator. So we multiplied 1 plus root 3 and when we do this ends up being upstairs. What do we have? We have root 3 plus 3 plus 1 plus root 3, just distributing that numerator. And the denominator ends up being kind of a nice and easy. It ends up being 1 minus 3. Altogether, what do we have? Upstairs we have 4 plus 2 root 3. In the denominator we have negative 2. So we divide each of those terms in the numerator by -2. Being -2 minus √3. Therefore, a equals, be careful, a is not -2. If it's in this form, and it does look like that, minus a minus √b. And so therefore a is +2 because it's -2. And then b equals. Okay, if sine alpha is 5/13, where alpha is between pi halves and pi, cos beta is -4/5. Beta is between pi halves and pi. Determine the exact value of sine alpha minus beta. All right, so we have two little Cartesian grids that we should draw to draw each of these situations. Keep in mind we want to look for how this domain is restricted to see what quadrant we're working in, because sine is +5/13. Because sine is positive, this could be either quadrant 1 or 2, but this right here tells us that we are in quadrant 1 for this. Sorry, between pi halves and pi, we are in quadrant 2 for this. Between pi halves and pi, we are in quadrant 2. So if sine is +5/13, then let's do a quick sketch of this. Sine is +5/13, so y/r ends up looking like this. This is x. We should label this as alpha. And let's start off with the fact that x squared plus 5 squared equals 13 squared. Squared equals 169 minus 25. X squared is equal to 144, so therefore x is equal to ±12. Now, because we're working in quadrant 2, and you do need to show this step, because we're working in quadrant 2, therefore x is the -1. We are told that sine alpha is 5/13, but now we know also that cos alpha is, now we know our x value is -12, so cos alpha is -12/13. Okay, so there's the first part. Next part, let's use cos beta is -4/5. We are also working in quadrant 2 because beta is between pi halves and pi. When I sketch this, -4/5. Cosine is adjacent over hypotenuse. It's your x over your r. And if this is 5 for your hypotenuse, this is -4. When we deal with this, we have y 4 squared plus y squared is equal to 5 squared. Y squared equals 25 minus 16. Y squared is equal to ±3, but we're in quadrant 2, or y is equal to +3. We know that cos beta is -4/5. Therefore, now we know sine beta. Therefore, sine beta is equal to 3/5. Now we're ready to go. To determine the exact value of sine of alpha minus beta, Our formula says sine of alpha minus beta is equal to sine alpha cos beta minus cos alpha sine beta. And now we know all four of those pieces. Sine alpha is 5/13. Cos beta is negative 12/13. No, it's not. Delete, delete. My mistake. 5/13 is sine alpha cos beta is negative 4/5. Thank you. Minus cos alpha is negative 12/13 times sine beta is 3/5. We add this together, we end up with. Don't simplify this yet, by the way. So yes, you could divide out the 5s and you'd have 4/13, but unless this is going to simplify this way, we are going to want a common denominator. So this ends up being negative 20/65 plus 36/65. Adding this together, this ends up being 16/65. Last one here, question number 5. Simplify sine 160 cos 20 plus cos 160 sine 20. So this question is kind of going at it backwards. It's going to run through this formula, but identifying that this looks like one of our sum and difference formulas. So we can say, we can notice that we are adding these. We have sine times cos plus cos times sine. So this is your sine formula for sine A plus B is equal to sine A cos B cos A sine B. So therefore, given sine 160 cos 20 cos 160 sine 20, therefore your A is 160 degrees, your B is 20 degrees. And so this fits this formula, and so this ends up being sine of 160 plus 20. Add that together, simplify. This is sine of 180 degrees, which is 0. All right, thanks so much. Good luck to you with your work. If you have any questions, please let me know.